Welcome back to this module on exploiting TLP to improve Unicode throughput. The purpose of this lesson is to give some examples of interleaved multi-threaded processes. Let's now have a look at some examples of fine-grained multi-threaded processes or interleaved multi-threaded processes. A very well-known example is the Sun Ultraspar T1, also called, during development it was called Niagara. It was targeted at commercial server workloads, for example, web-based applications, online transaction processing, enterprise resource planning. Features of such applications, of such commercial workloads, are that they have huge working sets and very poor locality. That means that the performance is memory limited, because very often the thread incurs a cache miss because the working set is too large to fit in the level 1 cache, and while that cache miss is being handled, we execute another thread. So the basic design is to use multithreading to hide the memory latency and to achieve higher throughput with lower single thread performance. This shows a die photo of the Niagara processor. It can be seen that it contains, 8 cores, and each of these cores is 4-way multi-threaded. This figure illustrates the pipeline of every single core. It implements fine-grained multithreading, interleaved multithreading, and it uses the canonical 5-stage pipeline plus one extra stage called the thread select stage. And the thread selector selects the thread to fetch and decode every cycle. Basically, it's round robin, but it's also sensitive to instruction latency. So if an instruction has a relatively long latency, it doesn't make sense to keep issuing instructions from that thread because the execution unit is busy executing this long latency instruction. And furthermore, it doesn't perform dynamic branch prediction that we discussed before, but static branch prediction. This brings me to a special kind of interleaved multi-threaded processes named barrel processes. Barrel processes are basically interleaved multi-threaded processes where the number of threads is sufficiently large to fill the entire pipeline with instructions from different threads. That means, as I explained before, we do not need to forward or detect hazards. All of it, that complexity is hidden by employing interleaved multithreading. Furthermore, the number of threads can be so large that there is even no need for a cache because the entire memory latency can be hidden. Or the cache can be extremely large, and large structures typically have a very long access time, and therefore the cache can be slow. Control hazards are also solved by multithreading. At the time the control hazard is resolved, when the branch has executed, we know the direction and we know the branch target, so the hardware can fetch the instruction at the branch target address. Barrel processes can potentially achieve very high throughput, number of instructions per cycle, but the single thread performance is really low. Here I illustrate a barrel processor where we have 32 PCs, where the number of register files is also 32, and of course in the write back stage we also access 32 register files. Let me briefly give some examples of barrel processes. For example, the CDC 6600 I/O processor, which was produced even in the 1960s. It had 10 virtual I/O processors. Now we would say 10 hardware threads, 10 hardware contexts. It employed a fixed interleave on a simple pipeline, and the cycle time of the pipeline was 100 nanoseconds, which is extremely slow nowadays, but at that time was very fast. And each virtual processor executes one instruction every 1000 nanoseconds. So every 10 pipeline stages, and it had an accumulator-based instruction set where we have an implicit accumulator that is the source and destination of most instructions to reduce the processor state, so that we don't need a full architectural register file that needs to be on chip. Another barrel processor was the Dinelcore HEP, heterogeneous element processor, which was developed in the early 80s. It had up to 16 processing elements, PE, and each of these PE had an 8-stage pipeline. And there was a different thread in each pipeline state. That means we need at least 8 threads. Again, like I illustrated a few slides ago, no forwarding, no hazard detection, but also no stalling and no flushing. It didn't even have cache. The memory was accessed directly through a switching network, a switch network. And the maximum throughput for 8 threads was 10 MIPS, million instructions per second, which of course nowadays is a very low number, but at that time was a significant throughput. Another example of a barrel processor was the Terra MTA, which was a multi-thread processor with up to 256 processing elements, and each of these processing elements supported 128 instruction streams or I streams. Now we would call that threads. That means it had 128 program counters and an astonishing number of 4096 registers. And an iStream instruction was allowed to issue if it had absolutely no dependencies with an instruction that is currently in the pipeline. And to be able to implement this very fast, a look-ahead field was added to every instruction, which indicated the number of instructions following the current instruction that have no dependencies with it in the current thread. Finally, I would like to remark that NVIDIA GPUs are also similar to barrel processors. NVIDIA graphics processing units, but I will talk about them later in a different specialization, multi-core specialization, are also very similar to barrel processors in that they try to hide the memory latency by extensive multithreading. This concludes this lesson. Thank you for watching. In the next lesson, I will discuss yet another form of hardware multithreading called simultaneous multithreading, or SMT. Hope to see you back.